Okay, so last time we wrote down the following integral, which was at one loop. So, for one loop integral, we had defined this integral I, d and m. So, d is the number of dimensions, n is the number of propagators, and I will show you what m is. And this was in Euclidean space, right, after the Wick rotation. Okay, and if you remember, we had dropped the I epsilon because it is not needed as we are working in the Euclidean space. But if you go back and search, it would be plus I epsilon. Okay, if you keep it, then it will be plus I epsilon. Okay, it's not really needed here, but it will be useful when we continue back to the Minkowski space. Okay, that's why I have kept it back. But as far as this integral, it is not needed. Okay, and also recall that L naught was I times L Euclidean. In fact, it was n. Okay, that is the nth component. So, 0th component in the Minkowski space, we call it the nth component of the vector L Euclidean. Okay, and the remaining special components here, they are identical. So, L E, the special components of Euclidean vector L, they are same on the both sides. Okay, I should be writing k, not L. Okay, these are the special components. Okay. Also, we because of this factor of phi, when I am doing one loop integrals, I am always going to get a factor of phi. Okay. So, the original integral which is in Minkowski space, that will lead to this integral together with a factor of phi. So, let me include that here. Okay, and we have seen that the result is this. So, this I is here, and we evaluated this last time, and we found that it is minus 1 to the n, where n is the number of propagators. M square depends on the external momenta. Okay, let me just write m square. I will then explicitly write the arguments times okay, that was the result. Now, when you are doing these Feynman integrals, you would want the result in the Minkowski space directly. So, what I am going to do now is continue this result to the Minkowski space by rotating back to theta equal to 0. You remember what that theta is? Where did that go? So, somewhere here, I am not finding it. Let us check. We had written an expression with e to the 2 I theta. We had multiplied these the time components with e to the I theta, and let us see if I can find. here. This is the denominator that we had at the time after weak rotation. This is for arbitrary theta, but if you rotate by 90 degrees, you get the weak rotated integral. So, I am going to put theta equal to 0 again. Okay, that is what I am doing. So, I am going back to the original integral. Okay. So, rotate back to theta equal to 0. So, what will happen? I d d k Euclidean, okay, there is only one factor of I because only one of the components was time component, okay, of the d components. So, that goes back to d d k. Okay, this is Minkowskian on the right hand side. What happens to the denominator here in the integrand? So, minus k e square minus m square plus I epsilon, okay, power n, that goes to what? That is what we should determine, and that is easy. Minus k e square, okay, is minus k Euclidean n square, okay, that is the nth component, and then you have minus k Euclidean square, okay, that is the vector. So, when you use this, you get that minus k e square, this becomes k e n, that has a I k 0, I square is minus 1. So, that kills this minus 1 and it gives you k 0 square minus k vector square, and this is k square. Okay. And so, as far as this is concerned, I know that minus k square should be replaced by k square, okay, when I rotate back. How about minus m square? So, let us look at minus m square plus I epsilon, and remember what is m square. M square is a function of p I dot p j, these are Euclidean, and m squares, and also depend on x i's, okay, these Feynman parameters. So, let me write down minus m square p I dot p j. M square depends on these objects, okay, plus I epsilon, that will go to what? It will go to minus m square. So, p I dot p j will be p I n p j n, this is still Euclidean, okay. So, I will put Euclidean here, these are the nth components, and then the other components. Okay. Now, when you rotate, as we saw just now, this will become minus p I 0, p j 0. Okay. So, this upon rotation will give you minus p I dot p j. Okay, I pulled out a minus sign. Now, this is in Minkowski space. So, minus m square of minus p I dot p j m square x I plus I epsilon. Okay, earlier I was writing m square because m square was positive definite. So, it made sense to write m square using the square as a symbol to remind it that is a positive object. But now, once you have gone to Minkowski space, this m square with these arguments is not necessarily positive definite. Okay. So, I will change, I will redefine it to make a better symbol. So, I will define this as this I will define as minus delta. Okay. So, what is delta? Delta is the continued version of m square to theta equal to 0. Okay. Whatever the functional form of m square is, that is what I am calling delta. Okay. So, minus m square plus I epsilon, after rotating back, it gives you minus delta plus I epsilon. Okay. And what is delta? Delta is same function m square continued to Minkowski space. Okay. So, what do we get then? The integral becomes or better still here this one. So, when I look at this after continuation, this has become the following. And there is a factor of I that will come from here. Okay. So, this I will be gone because I ddke goes to ddk. So, you get the integral on the left hand side of, so this is the left hand side and this result I am calling right hand side. Okay. So, how do I get rid of this? So, you get integral d dk over 2 pi to the d 1 over k square minus delta plus I epsilon to the n. Okay. This is after continuing that integral. So, now I can take the result that I had, the specific result here, okay, this one, and also continue it and see what I get. So, all I have to do is take this m square and continue it, and I already know what m square becomes. M square is what I call delta. Okay. Just replace wherever in m square you have these things, and continue it to complex, continue it to the Minkowski space. So, this will be the replacement, and here I will get the same, everything will be same except m square will be replaced by delta. So, you get I times minus 1 power n 1 over 4 pi d over 2 gamma n minus d over 2 over gamma n times 1 over delta minus I epsilon. Okay. You will see that you get a minus I epsilon, okay, because I am pulling out that minus sign. Yeah. So, here I will just explain why there is minus epsilon. So, here you see the this is minus m square. So, whatever is in front of this minus is what enters here. Okay. If you keep that I epsilon also, then it will be minus of m square minus I epsilon. So, here m square minus I epsilon, and it is this minus m square minus I epsilon, which has become delta minus I epsilon. Okay. So, this is the result. I wish I had written it more nicely, which I think I should do. Okay, let me write it again. So, we have shown that. So, the result in Minkowski space is d dk over 2 pi to the d. Okay, I am going to use this result again, and that is why I want to write it nicely. K square minus delta plus epsilon power n, where delta depends on all those variables which I listed, I minus 1 to the n over 4 pi d over 2 gamma n minus d over 2 over gamma n times epsilon n minus d over 2. Okay, so good. You can directly use these results when you are doing Feynman integral instead of first going to Euclidean space and then doing continuation, because that is exactly what is done here. Now, I will also give you another result which will be useful. Which is the following. So, I want to evaluate now a different integral over k square plus 2 p dot k minus delta minus plus epsilon to the n. Okay, what is the result for this? And it is very easy to do, but before I show you what the result is, actually I should not even show you, you should do it yourself. But look here, the delta contains the dot products. Okay, delta is a scalar. So, it contains the dot products of all the external momenta. Now, here p is some momentum in the problem and external momentum in the problem, or even a linear combination of them, and the p is sitting here. Okay. Now, this integral, if you see, this is a Lorentz invariant integral. Okay. Now, the result can only depend on p, because k is anyway dummy, right? This is integrated over. So, result can only depend on p, and the only function that you can construct given only one momentum, which is a scalar, is p square. Okay. So, whatever I do, the result of this will be a function of p square. So, I leave it as an exercise to just do the change of variables. Okay. By first you complete the square and then do a change of variable and write it as the following. So, this will become d dl over 2 pi to the d. Okay, I am just giving you the result of what will happen after completing the square and changing variables. Okay, this you should check. Okay, now you already see that after doing those steps, p square has appeared in here. Now, instead of having 2 p dot k, you have p square plus delta. Okay. So, clearly when I integrate, the result will depend on p square and delta, and this is equal to, let me try doing it, pulling it out. This is equal to, so this is a result you already know, right? We had on the previous page. Think of this as delta prime, okay, and then use that result and you get I minus 1 to the n over 4 pi d over 2 gamma n minus d over 2 over gamma n and you have 1 over p square plus delta minus I epsilon and minus d over 2. Okay, that is the result. So, you have these two important results. Now, when you are doing quantum electrodynamics, okay, or theories which have spin, then you can get powers of k in the numerator also. Okay, even though we are not doing it in this course, but let me still record that result. So, for those of you who have already seen, I mean, some are familiar to some extent with quantum electrodynamics, will know that you have when you are looking at the propagator, you get 1 over what happened. You get 1 over k slash minus m, where k slash is just k mu gamma mu. Okay. And when you write the propagator with k square minus m square in the denominator, then you get things like k slash in the numerator, okay, which is just k mu gamma mu. So, you will have integrals which will involve k mu in the numerator. Okay. So, let us look at one of those. So, I want to integrate d dk over 2 pi to the d k mu over k square plus 2 p dot k minus delta plus epsilon. Okay. What will be the result? So, before I give you the result, let us see what it will look like, at least the p dependence. So, again using the same argument, the result will depend on delta. Okay, delta is a scalar, it is made out of all the invariants and m squares and whatever and xi's. Now, this integral carries a index mu, okay, that is a Lorentz index mu. So, whatever you get after the integral should also carry that index mu, right, because it is a Lorentz index. This object transforms like a 4 vector or like a d vector because we are in d dimensions. So, it should carry that index mu. Now, there is only one object that can carry that index mu, since k is dummy, it will not appear, and you will have p. So, result should be proportional to p mu times something. Okay. So, it should be proportional to p mu, that much we can say. And now, let us figure out what it is. So, the trick is, let us call it I, let me put an index mu. Okay. Let me take a derivative of this integral with respect to p mu. So, I evaluate del over del p mu, where mu is the lower index now, okay, of this integral, of not this integral, but without k mu. Okay. So, let us evaluate. Okay, so this integral, what I have here in this line, this we already know, that we have seen here. Here we have already evaluated this one. So, that is known. I can take a derivative with respect to p mu. So, I take the expression and take the derivative. So, I can do that easily. But now, let us see what it generates when I do this integral. Okay. So, this will give you integral d dk over 2 pi to the d So, this is basically, this will give you minus n over k square plus 2 p dot k minus delta plus I epsilon power n plus 1 into 2 k mu. Okay. Differentiating this will give you 2 k mu. So, that is what you get. Now, I will just, because I want to evaluate this integral with n, and what I have gotten is almost the same integral other than some constants, but with the power n plus 1. So, I will just change n to n minus 1 in this expression. Okay. So, what I get is, so change, let n go to n minus 1. So, I get integral d dk over 2 pi to the d k mu over k square plus 2 p dot k minus delta plus I epsilon power n. This is what we want to evaluate. Okay. This object. Okay. And this is, we divide by 2, 1 over 2. This n, I am changing n to minus n minus 1. So, this will become 1 over minus n plus 1. Okay. That is fine. Then you have a derivative of with respect to p mu of the result of after integration, which is I times minus 1 power n minus 1. So, what I am doing is I am taking this result and putting n equal to n minus 1. Okay. That is what I am doing. N minus 1, 1 over 4 pi d over 2 gamma n minus 1 minus d over 2 over gamma n minus 1 times 1 over p square plus delta minus I epsilon power n minus 1 minus d over 2. Okay. And if you use z gamma z equal to gamma z plus 1. So, here you have gamma n minus 1, this is minus of n minus 1. So, n minus 1 times gamma n minus 1 will give you gamma n. Okay. So, use that, and this will give you finally p mu. Taking a derivative from this thing, it will give you, so the final result I am writing, you can check, minus p mu minus p mu. So, as I said, the result will be proportional to p mu. So, that is what we have got, times I minus 1 power n over 4 pi d over 2 gamma n minus d over 2 over gamma n 1 over p square plus delta minus I epsilon okay, n minus d over 2. That is what you get. So, what you have here in the square brackets is exactly what we had here. Okay, it is identical. So, the result is, this is the explicit result, but if I were to relate the two results, then it is the following. So, integral d dk over 2 pi d k mu over k square plus 2p dot k minus delta plus I epsilon power n is equal to p minus p mu times the integral without k mu, okay, the scalar integral d dk over 2 pi d okay. These are very useful results. We should keep them safe. Okay, so this is nice. We have several. What happened? Okay, there is an extra page here. I'll delete it later. Okay, now that we are doing these integrals, I will also show you, give another result to you. So you will also encounter integrals of this kind when you are doing loop integrals. d dk over 2 pi d k mu k nu. So you may have two factors of k in the numerator and then the same denominator. Okay, so let us see even before doing any explicit calculation, what the result would look like as far as its mu nu dependence is concerned. Okay. So this integral is a rank 2 integral. I mean the result should be a rank 2 tensor because you have two indices mu and nu. Okay. But that those indices cannot depend on, I mean k is dummy. So those indices can only appear on p, right. That is the only vector you have here. There is nothing else that you have. And the dependence should be such that the integral that you get, the tensor that you get is symmetric. See, this is if you interchange mu with nu and nu with mu, integral does not change, right, because k mu is same as k mu k nu. These are numbers, right, k0 k1 some number, k1 k0 same number. Okay. So you can interchange. So the result should be a rank 2, a symmetric rank 2 tensor. Okay, that is one thing I know from here. Now, what are all possible rank 2 tensors available to us when we are doing this integral? So, given that the result can depend on p, we have this rank 2 tensor available to us, which is symmetric under interchange of mu and nu. There is another rank 2 tensor which is always available, which is g mu nu, or better I should call it eta mu nu, but let me call it g mu nu. Okay. So, that is your metric tensor which is always available. So, whatever this result is, it has to be some constant which I will call A times p mu p nu plus some constant b, and that constant b will depend on delta and all those other variables, okay, n, d, all those things. But the general form has to be this. Okay. So, I will leave it as an exercise to find out the explicit answer using these kind of tricks. What has happened here? Yeah. Why did I jump to the next page? Okay, anyway. So, please do this, you know the trick of differentiating, and you can try to figure this out. I will, instead of giving the answer for this one, I will do a simpler version. Okay, this you figure out. Exercise, find A and B. So, now what I will do is I will put p equal to 0, so that I can evaluate this integral in a slightly simpler setting. Okay, so, p is gone. So, of course, the result will not depend on this factor because p is 0 now. So, let us look at this integral d dk over 2 pi d k mu k nu over k square plus 2 p dot k, k square minus delta plus I epsilon power n. Okay. So, I already know that this result should be proportional to G mu nu, because that is the only thing that will be left now. But there is another thing that you see is that if I contract this with G mu nu, okay, this G mu nu times k mu k nu is k square. Okay. So, this integral becomes d dk over 2 pi d k square over this factor. Okay. Now, let me write it this way. So, it is G mu nu. I claim that this can be written as the following. Let us see whether the claim is correct. Okay. G mu nu is fine, that I have already convinced you, but this integral is some function of, it is some constant, right. It involves all these deltas and d's and n's, but some constant. So, it is consistent with whatever I said earlier, that the result should be proportional to G mu nu. But whether it should be k square here, whether the integrand is correct or not, let us check. So, if I contract on both sides with G mu nu, left hand side will give you k square over this. If I contract with G mu nu, this G mu nu times the other G mu nu will give you some constant, and then exactly here k square as you had here. So, it is clear that the form of the integral is correct, that I should get G mu nu times this kind of an integral, but what is not necessarily correct is the some constant which could appear here, okay, some number which could appear here. So, let us find out that contracting on both sides with G mu nu, it will produce k square here, and here it will, you already have k square, but G mu nu will be what is delta mu mu, okay, which is if you were in integral number of dimensions 4, 5, 6, 10, whatever, 20, 100, then this will be just 1 plus 1 those many times, right. So, if d is integer, then this is just d, and even when d is not integral, okay, it is consistent to define G mu nu to be equal to d. Okay. So, I will not go in more details about these issues of dimensional regularization, but it is consistent to define G mu nu to be d, and the other things related to when you have spinor fields, but that is not what is bothering us in this lecture. But if you are interested, you should look at the book by John Collins, okay, on renormalization. So, anyway, now let us fix the factor of C. So, when I multiply G mu nu both sides, it will give you d. So, clearly C should be 1 over d, that is what I should use. Okay. So, I will remove that C and put a 1 over d. Let me write that result also. This is I want to okay. So, now here, so what I have shown you is integral d dk over 2 pi d k mu k nu over k square minus delta plus I epsilon to the n is equal to 1 over d g mu nu, sorry, indices should be up because on the left hand side you have the indices up, d dk over 2 pi d k square over k square minus delta plus I epsilon power n. Okay, so these are some useful integrals that you will encounter when you are doing loop integrals. Okay, and I will stop here. There is one more thing I wanted to tell which I forgot. Yeah, this is something I should have told you much earlier. Yeah, here after this. So I'll add a slide here. Okay. So yeah, here we had looked at the volume integral and we found explicit expression, but I will also tell you how to parameterize. Okay. So we had d, or I think at that time I was using n, d n k e, n dimensions. Okay. This is dk Euclidean 1, dk Euclidean 2, and so forth, dk Euclidean n. Okay. So this is n dimensional. Okay. So you have n variables, k e1, k e2, so forth up to k en. Okay. And we want to use spherical coordinates. Okay. Because most of these integrals have no dependence on angle, they only care about the magnitude of k. Okay. They involve things like this. So if you look at k e1 square, k e2 square up to k e n square, okay, then that is a constant. Okay. So r I will, or maybe small r squares. Okay. So if you have spherical symmetry, then we will use this radial coordinate, okay, and the sum of these squares will be equal to the radius square. Now there are total of n variables. One of the variables I can choose as r. So I am going to do a change of variables from this set to another set of which one of them is r, and I claim that I can introduce n minus 1 angular variables. Okay, that's something I can do. You can parameterize differently also, but one of the parameterization is that you have one length in the problem, one coordinate which has dimensions of length in the problem, and all others are dimensionless. Okay. But this is not the only way. You can do different parameterizations where maybe two of them has dimensions of length and others have dimensions of, others are dimensionless like angles. Okay. But this is one of them which is allowed, and let me give an explicit expression which tells you that you can make such a choice. Okay. So here is the explicit result. So k e 1 r cos theta 1. Okay. K e 2 is r sin theta 1 cos theta 2. Okay, let me, even though I am going to write exactly the same thing, I want to write it in a different order, it will be useful. So, k e n, the nth component, I will parameterize as r sin theta 1, sin theta 2, so forth, sin theta n minus 3, sin theta n minus 2, sin theta n minus 1. Okay. So, if sin theta 1, sin theta 2 and so forth up to here, then k e n minus 1 I am parameterizing as r sin theta 1, sin theta 2 and so forth, sin theta n minus 3, sin theta n minus 2, cos theta n minus 1. Okay. I will soon tell you why I have done it this way. K e n minus 2, the n minus 2th component, I will parameterize as sin theta 1, sin theta n minus 3, cos theta n minus 2. Okay. And you continue like this, then you have x 3 is equal to r sin theta 1, okay, then sin theta 2, then cos theta 3, sorry, not x 3, k e 3, okay, and k e 2 is equal to r sin theta 1 cos theta 2, and k e 1 is equal to r cos theta 1. Okay. And let us see whether this is a parameterization that is going to work. Okay. And I want to have this. So, if I sum the squares, I should get r square, a constant. Okay. And that would mean that I am using a spherical coordinate system. So, let us take k e n and square it, and take k e n minus 1 and square it and add the 2. So, I am adding this one and the previous one. Okay. So, you will have r square sin square theta 1 squares of all these plus, times cos square theta n minus 1, and here k e n, when you square, you get exactly the same factors. R square you got here, here also you get r square, sin square theta 1, sin square theta 1, sin square up to sin square theta n minus 2, sin square theta n minus 2, but here you had cos square theta n minus 1, and this one has sin square theta n minus 1. So, when you add the two, the squares of these factors in both, they are common. Okay. So, you can pull them out and you are left with cos square theta n minus 1, cos square sin square theta n minus 1, that adds up to 1, right. Cos square theta plus sin square theta is 1. So, what you are left with is k e n minus 1 square plus k e n square will be just r square sin square theta 1 up to sin square theta n minus 2. Now, you add that with k e n minus 2 square. Okay. So, when you do that, you see that again the same factors. Here you r square, here is r square, here you get sin square theta 1, sin square theta 1 up to sin square theta n minus 3, sin square theta n minus 3. So, that in the sum you can factor this out and you will be left with cos square theta n minus 2, sin square theta n minus 2, and adding these two makes 1. So, you see every time you are adding a square of the previous coordinate, the last angle is dropping out. Okay. So, if you continue this way, you will eventually arrive here at this stage, you will arrive at, when you have added the sum of all these squares up to k e 2 square, you will have r square sin square theta. Okay. That cos square theta 2 would have already been taken care of by this sin square theta 2. Okay. So, at the end you will be left with from this I mean this plus all the remaining will give you r square sin square theta, and k e 1 square is r square cos square theta 1, summing the two will give you r square, and thus we get this one. So, this is the parameterization in n dimensions when you are looking at spherical coordinate system. Okay, that is something I wanted to tell you, which I had missed. Okay, good then. So, we have done most of the integrals that are usually required, and now I can start discussing more about renormalization and getting rid of infinities. See you in the next video.